Let's recall we introduced three cycles earlier in this class. They're power cycle, refrigeration cycle, and heat pump cycle. And now we're going to apply second law of thermodynamics to those three cycles. We will start from power cycle first. First of all, let's sketch a power cycle. You can think of the engine in the car as an example for a power cycle. The purpose of a power cycle is to generate mechanical work. You burn the gas in the car, so you provide heat, we call QH, and it's delivered to the engine at a high temperature, we call it TH. And then you convert as much of QH as possible to mechanical work. We call it W cycle. And then second law tells us you have to lose heat to the environment. We call it QC, and to the lower temperature, T cold, which is usually the temperature of the environment. And from second law, we know QC will never be zero. QC will always be there. You have to lose heat. And then the second part, let's apply the definition of efficiency we call eta. The definition of efficiency is purpose over cost. The purpose of the engine is to deliver mechanical work. W cycle is the purpose of this cycle. The cost is the heat generated from combustion, which is QH. And then we can rewrite W cycle from conservation of energy equation. W cycle must be equal to QH minus QC over QH, and the solution is 1 minus QC over QH. Because QC will never be zero, so the second term in the right-hand side will always be positive. 1 minus something positive must be less than 1. So that's why the efficiency of the engine will never be higher than 100%. So the next question is, if the highest efficiency will never be 100%, then how high can it be? The maximum efficiency, we call it eta max, is equal to 1 minus Tc over Th. Tc is usually the ambient temperature. Th is usually the combustion temperature. We will prove this equation later on in chapter 6. And eta max will always be greater than or equal to the actual efficiency. We use eta for actual efficiency. When do we have this equal sign? Eta will be equal to eta max if the process is reversible. That's when you have the maximum efficiency. And then number 4. All reversible power cycles between the same TH and TC have the same efficiency. Why? Because if the process is reversible, that means eta must be equal to eta max, and eta max is only a function of Tc and Th. So if the Tc and the Th are the same, no matter what kind of engine you have, the efficiency will always be the same. So that's how we apply second law to a power cycle. And next, we do something very similar. we will apply second law to refrigeration cycle and heat pump cycle. How do we sketch a refrigerant cycle or a heat pump cycle? If you can recall, the two cycles actually share exactly the same diagram. You can think of the refrigerator in the kitchen as one example. What it's gonna do is it will grab the heat, it will absorb the heat from the cold inside of the refrigerator. So we call it QC, and it's at a low temperature, so we call it TC. The refrigerator will absorb the heat QC at low temperature T cold, and then release this heat to the outside of the refrigerator, which is at a higher temperature. We call it TH. So now you can see heat transfer happens from low temperature to high temperature. And from second law, we know this will never happen naturally. So if you want heat to be transferred from low temperature to high temperature, you have to pay. And what do you pay? Electricity, which is one format of work. We call it W cycle. And the heating cycle shares exactly the same diagram. How does the heating cycle work? Heating cycle absorbs heat, QC, from the cold outside of your house, which is at very cold temperature, we call TC, and then releases the heat to the warm inside of your house. We call it TH, which is at a higher temperature, TH. And heat transfer will never happen from cold to hot unless you pay. So again, we pay electricity, which is W cycle. So that's why the two cycles have exactly the same diagram. The difference is the purpose. For a refrigeration cycle, the purpose is to keep cool. Which one is the direct reason to keep it cool? It's QC. However, when you move on to a heating cycle, the purpose is to keep your house warm. And what is the direct reason that your house can be kept warm? It's QH. To measure the performance of each one, we introduced beta and gamma. Beta and gamma have the same name. They're both called coefficient of performance, and they have exactly the same definition as efficiency. It's purpose over cost. For a refrigeration cycle, we use beta, and the purpose over cost. Purpose for a refrigeration cycle is keep something cool, which is Q cold, divided by cost, which is W cycle. And for a heating cycle, we use gamma for coefficient of performance. What is the purpose of the heating cycle? To keep the house warm, and that is QH. The cost will still be W cycle. And then from energy balance equation, just in case you forget what is energy balance equation, total energy going in, so that's QC plus W cycle, must be equal to total energy leaving, so that is QH. From this equation, we can rewrite W cycle. W cycle can be rewritten to QH minus QC. So we want beta and gamma to be as big as possible. The bigger the beta and gamma are, the better your performance is. So next question is, how big can they go? So we introduce beta max and gamma max. Just like efficiency, there's an upper limit for them. Beta max is to change Q to T. So it's Tc over Th minus Tc. And then same thing for gamma. Gamma max is equal to Th over Th minus Tc. It's very easy. You just change Q to T, then you can find the maximum value. We can approve those two equations later on in chapter 6. Okay, from second law, we know W cycle can never be zero because if you want heat to be transferred from low temperature to high temperature, you have to pay something. And what do we pay? We pay electricity, which is W cycle. So this term will never be zero because of second law. And then beta will always be less than or equal to beta max. And a gamma will always be less than or equal to gamma max. And the equal sign is true if the process is reversible, just like before. And then one more thing. Our reversible refrigeration, or heat pump cycles operating between the same TH and TC have the same beta and gamma. Why? Same as before. Because if the process is reversible, beta is equal to beta max and gamma is equal to gamma max. And then you can take a look, beta max and gamma max, they are functions of Tc and Th. So if you have the same Tc and Th, no matter what kind of design you will have the same beta max and the same gamma max.